All right, all right, all right. Welcome back to the coronavirus bunker for the next installment of Math 341. I hope you guys don't mind, but I'm probably going to be in the habit of posting the lecture for the Monday, Wednesday, and Friday, probably the day or evening before. My kids are now starting homeschooling, which means not only have I gone from being an in-classroom lecturer to now an amateur video producer, but I am also my kid's teacher, sort of, more or less, for the next 2 months. So, life got a lot busier for me, despite the fact that I don't go anywhere or do anything. Right. So I'll probably be trying to post them the evening before, and of course, as always, if you have any questions, feel free to email me or send a carrier. Actually, don't send a carrier pigeon. Birds are dirty. Okay. So last time we had just finished discussing characterization of cluster points. Okay, and an extensive discussion of cluster points. So now we're a little bit behind, lecture relative to notes. So I had posted a set of notes on Friday, which are labeled with Friday's date, 3/27/20, and we didn't actually get to any of those. So that's what we're going to cover here today, and I did make up one extra page's worth of notes in case we do get to some examples. I hope we will. I think we will. Okay, so without further ado, let's make the following definition. So I want to define what it means to have the limit as x approaches c of a function f of x. So let f be a function from some set a to r. Let's be pedantic. Be a function and let c be a cluster point of A. So this whole thing, I guess, should be definition. So let A be a function, or sorry, f from A to R be a function, and let C be a cluster point of A. Then the limit as x approaches C of f of x is equal to L if, it's got a kind of familiar flavor, if for all epsilon greater than 0. But here the similarity kind of ends. There exists so when we were talking about limits of sequences, at this point we would say for all epsilon greater than 0, there exists a natural number, a really big natural number, such that if we go out far enough in the sequence, past this natural number, good things happen. Okay? Now, instead of going out really far in the sequence, the idea is that we're going to go really, really close to this point C. We're going to have x be very, very close to C. And close means we need to say how close, okay? So if for all epsilon greater than 0, there exists a delta depending on epsilon greater than 0, such that the distance from f of x to L is less than epsilon, so that's what we want. We want f of x to be very, very close to L if if x is very, very close to c, and the sense in which it will be very close to c is as follows. The absolute value of x minus c will be strictly less than delta of epsilon and, somewhat pedantically, greater than 0. And all this greater than 0 thing is saying is that we want values of x that are really, really close to c, in this sense, but are different from c, right? All that, this saying that this absolute value here is greater than 0 just says that x is not equal to c. That's all, okay? So that is the definition of the limit as x approaches c of f of x is equal to L, right? This limit is equal to L if, for all epsilon greater than 0, there is some delta greater than 0 such that the distance from f of x to L is less than epsilon if the distance from x to c is less than delta and bigger than 0. Okay, so you should really think of that as an afterthought. That's kind of the thing that everyone forgets and then gets 4.5 out of 5 when I ask you to give the definition of the limit as x approaches c of f of x is equal to L. I guarantee, and indeed, it says so, right here in the notes, which have already been posted on the internet for 5 points. This is the first question on the final exam. Let f from a to r be a function, and let c be a cluster point of a. What is the definition of the limit as x approaches c of f of x is equal to L? Okay? And there, on the board, is the answer. Okay? That is the answer to the first question on the final exam. It is worth 5 points. Very similar to the answer to the first question on the midterm. Also was worth 5 points. And while generally well done, you guys still did not become the record holders by having everyone get it right. So there's still a chance here, okay? This is going to be, and it's a take-home exam. Like, literally, okay? I'm telling you, this is the first question. I've also posted online that this is the first question. And on the next page of online notes, there's the answer at the top of the page. Okay? So I really think that if you don't manage to get those 5 points at the beginning of the final exam, you may want to go to like genealogy.com or something, because if you go back a couple of generations, you might be into the invertebrates. Okay? Please. You can get these 5 points. You can do it. All right. Let's see. So maybe I might not do things in exactly the order they appear in the notes. Let me next draw you a picture to try and give you a flavor of how this works, okay? So one thing I want to point out here is that I've written delta of epsilon, right? What this is saying is that how close x has to be to c depends on how close you want f of x to be to L. So I would like to draw a picture now that will hopefully make that a little clearer. And I'm sorry, I'm trying to stand on this side of the board. I mean, the lighting is not perfect down here. All right, so let's make a picture. So this is going to be my f of x, this function here. Let's say that this point here along the x-axis is c. Okay, and that this height here is L. And of course, as x gets closer and closer to c here, then you can see the function comes up closer and closer to L. And as far as limits go, this picture I've drawn is kind of a special one. Come on. As far as limits go, this picture I've drawn is kind of a special one because this is an example of what is called a continuous function, a definition we will also get to. Okay, but the idea is that there are no breaks in this function, so not only is the function headed towards something civilized and nice as x approaches c from either side, but in fact that something that it's headed for turns out to be the value of the function at that point. But we're not concerned with that right now. So what happens? You are given some tolerance, epsilon, and you would like the value of your function to be within epsilon of this number L. That means if this point is L plus epsilon and this point is L minus epsilon, then you want the height of your function to be somewhere inside this tube, right? The idea is that you want the height of the function somewhere in this tube, and the only thing you're allowed to control is how close you are to this point C, okay, along the x-axis, right? So, of course, if you choose a point that's not particularly close to C, like out here, and then you look up at the function, well, the value of the function lies outside that tube you just drew. The value of the function minus L, the absolute value of that is not less than epsilon. So that's no good, okay? But there is a chunk of the function here that sits entirely inside the tube. And as you can see, that occurs when you are close to the point C. So maybe, by looking at this picture, you could say that roughly, if your x value is somewhere in this vertical tube here, then if you go up to the graph of the function f of x, all of those function values will lie inside the prescribed horizontal tube from L plus epsilon down to L minus epsilon. Okay? So the width of this vertical tube here, that's where your delta of epsilon comes from. So this point, this right-hand endpoint here will be C plus delta of epsilon. And this left-hand endpoint will be C minus delta of epsilon. Okay? So if you would like, right, so here we're going to have that f of x minus L absolute value is less than epsilon if the absolute value of x minus c is less than delta of epsilon. Okay, and in fact that will be all the more true if we exclude the possibility that x is equal to c. Okay, so that's the picture of what's going on here. And then I hope you can imagine that if I took epsilon then, and I made it smaller, that is, if I took this horizontal tube and I shrank it, then it would be harder for the function to land inside that horizontal tube. It would still be possible, but it would be harder. And in order for the values of the function to land inside that now smaller horizontal tube, the x values that you plug in would have to be still closer to x equals c. right? So this vertical tube would also get narrower. And that's exactly why we write delta as a function of epsilon. In practice, in examples, it will occasionally be the case that you really do wind up producing some kind of a formula for delta in terms of epsilon. There is no one single formula for delta in terms of epsilon. Some of them work, but it's a little bit similar to what happens in the case of the limit of a sequence, right? If somebody gives you an epsilon, and you can find a delta of epsilon such that when x satisfies this inequality, then f of x satisfies this inequality, that's great. But then any smaller number here will also do the trick, right? That's what tells you that there isn't any one, there might be a sort of canonical or obvious choice for delta of epsilon, but there's no one right choice. Anytime you find something that works, anything smaller will also work, and that's similar to what happens with sequences. Once you find a big enough n of epsilon that works, any bigger n will also work, okay? So, there is a dependence, right? The smaller epsilon gets, in general, the smaller delta of epsilon gets. But there does not have to be a very hard and fast sort of formulaic connection between the two. And the way in which you make this connection will differ from example to example. Okay, clear as mud. Great. So the next thing the textbook covers is the idea that the limit is unique. I think before we do that, I'm just going to do a couple of the super basic examples, just because I think that's a little more pedagogically sound, as they say. So I don't know how things are where you are. Here in Tippecanoe County, we've got 11 cases now of coronavirus, and one unfortunate person has passed away. So hopefully where you are, you're doing all right. Okay. So let's start with the absolute most basic possible example. Let's say let b be a real number, then the limit as x approaches c of the constant function b is just the real number b. Okay, so a couple of things are implicit here, kind of being swept under the rug. One is the domain of the function, right? So the constant function, the function just equal to this number b in R, I suppose could be given whatever domain you want. But if nobody tells you what the domain is, then you should just assume that it's all of the real numbers, since it can be. Okay? Then similarly, it's not specified in the example what c is, right? However, we do know in general that when you write down the limit as x approaches c of a given function, that c had better be a cluster point of the domain of the function. Now, the domain is all of the real numbers, and the cluster points of the real numbers are all the real numbers. Again, it doesn't matter. So the domain is all the reals, and every single real number is a cluster point. So this all makes sense. So how do you answer this? Similar to questions about finding limits. 3 parts, okay? One is kind of pedantic and the same. Let epsilon greater than 0 be given. And as was the case for limits of sequences on the test, I will give you 1 point out of however many for just writing this down, Okay? Let epsilon greater than 0 be given. And as in the case of sequences, it's part 2 where all the real work is. Part 2 is to analyze the quantity f of x minus L, right? Which in our case, what is f of x? Well, f of x is just the constant function b, and L is also b. Okay? And so this is a particularly simple example because, of course, now f of x and L are in fact equal. Therefore, this quantity is equal to 0, which is less than epsilon for all x. So for any x. Okay? So here we have the incredibly rare situation where the distance from f of x to L is going to be less than epsilon, no matter where you are. It doesn't matter how close x is to c at all in this particular example. You're always going to get that f of x minus L absolute value is strictly less than epsilon. Okay? But, for the sake of completeness, you can just pick whatever delta you want. So, I'll write that for completeness. Let's choose delta of epsilon equal to 1. So, right, so that concludes part 2. We've done the analysis. We've looked at the quantity f of x minus L, absolute value. We figured out how close x has to be to c in order for that to happen. And then finally we come to part 3, which is just tying everything up with the bow. So f of x minus L equal to b minus b is less than epsilon if 0 less than x minus c is less than delta of epsilon. And so the limit, by definition, the limit as x approaches c of b is equal to b. Okay? So part 3 is essentially just demonstrating that you know what the definition of the limit as x approaches c of f of x is. Okay? So that is the simplest possible example that we could have. Let's go up 1 degree of complexity from here. Okay? Oh yeah. It's kind of like show and tell here. I mean, I've got all this stuff in the basement. I found this, though. This is amazing. I have no idea what's on here. Maybe I don't want to know. But this is like an original Sony Hi8 video camera. Back in the day, when you used to have to lug something this big around just to take like, I think this one took like 80 minutes of video. You could take 80 minutes of video with this thing before you had to replace the tape, which is actually still stuck in there. One of these days, maybe. Anyhow, I was trying to imagine with my kids this morning, you know, what are they going to say to their kids? Because, of course, my kids are complaining that they're bored. you know, we've been stuck inside the house for 2 weeks and there's nothing to do, blah, blah, blah. And of course, I do the curmudgeonly parent thing and I say, well, you know, you should be grateful. I mean, you've got phones, you've got Netflix, you've got Xbox. Like, we didn't have any of that stuff, you know? We just had like a piece of rope and a stick or whatever. I mean, TV only had good shows on for a couple of hours in the evening. Had to kind of entertain ourselves. But I was just wondering, you know, what's the equivalent going to be for them when they have kids, you know, and their kids are complaining there's nothing to do. It's like, what are they going to say? Well, you know, when I was a boy, we didn't have a jack in the back of our necks, and we had to eat our own food. There were no tubes, and cars didn't fly, and I can't imagine what the conversation will be like. I'm sure it will be entertaining. I'll be there to see it all with popcorn and no help whatsoever. I'm going to be that grandparent. I just hand them back when they start crying or complaining. Okay, next example. So let's say, let's be a little more complete here. Let's say that A, the domain of the function is all of the real numbers. And f, of course, is a function from A to R. And we'll just take the identity function this time. F of x is equal to x. Then I claim the limit as x approaches c. And again here, we don't have to worry about what c is exactly because the domain, once again, is all of the real numbers, right? And every single real number is a cluster point of the real number. So any c will do here. The limit as x approaches c of f of x is just equal to c itself, right? That's what we should have. All right, so let's prove that it's so. 1, let epsilon greater than 0 be given. Right? So there's 1 point out of however many right there. Okay, part 2. We want to analyze the quantity absolute value of f of x minus L, where L, of course, is what we think the limit is, and f of x is our given function. So in this case, it's going to be the absolute value of x minus c. And we want that to be less than epsilon. Okay? And what we have to keep in mind is that we are allowed to control something. So in the case of sequences, right, we wanted to control, instead of f of x, we had xn minus L. We wanted to control that. And the way we could control it was by insisting that that index, little n, be big enough. Okay, now instead we've got this slightly different thing, f of x minus L. And the way we can control it is by controlling how close x is to the point C. And another way of saying that is to say that we control how big this thing is. Absolute value of x minus c. And so one reason why this example then is particularly straightforward is that the thing we want to be small, f of x minus L, absolute value, actually turns out to be equal to the thing we know we can control, the thing we are allowed to control, the thing we are allowed to insist is less than a certain something, less than a delta of epsilon. So what this is telling us here is that if we want the absolute value of f of x minus L to be strictly less than epsilon, we should in fact just choose delta of epsilon to be equal to epsilon itself, because that will force this quantity to be less than epsilon, and that's exactly what we want. And so that's exactly what we will do. Let me not quite erase everything to try to have some continuity here. Okay, so let's say, set delta of epsilon equal to epsilon. And again, that's the end of step 2. Step 2 is consider the absolute value of f of x minus L. Observe that you would like that to be strictly less than epsilon, and then figure out how you can make that happen through imposing a condition on the size of absolute value of x minus c. Okay, and that condition is given by delta of epsilon. Here we figured out that delta of epsilon equal to epsilon will do the trick. Okay. Once you have figured out what that delta of epsilon should be, then you can move on to part 3, which is essentially just regurgitating the definition of the limit. Okay, so now I can erase this. So now, given epsilon greater than 0, set delta of epsilon equal to epsilon. Then, if the distance from x to c is less than delta of epsilon, we have that the distance from f of x to c is less than epsilon. And that's what we wanted. So the limit, by definition, as x approaches c of f of x is equal to c. Okay. So those are the two simplest possible examples of the definition of the limit of f of x as x approaches c in action. Okay. So, of course, you will not get a question quite that easy on the final exam, especially considering the fact that you will be able to look up all kinds of stuff. I imagine you will, anyway. So, let's have a look at a somewhat more challenging example. All right. So for this example, once again, we're going to have the domain be all of the real numbers, and of course f, a function from the domain into the real numbers, and f of x now will be given by the formula f of x equals x squared. Okay? And then what we would like to do is show that the limit as x approaches c of f of x is, well, I mean, we all know what the answer is, right? I mean, f of x in this case is a polynomial. If you would like to find the limit of a polynomial, Calc 1 tells you that you just go ahead and plug in whatever number you're headed for in the limit, and that's the answer. And that's because the polynomial is a continuous function. Okay, so the limit should be c squared. But what we're going to do here is prove that that is indeed the case, which turns out to be more complicated. Okay, so once again, first thing you do, let epsilon greater than 0 be given. Okay, for 1 point, let epsilon greater than 0 be given. Then 2, let's analyze f of x minus L absolute value, which in this case is going to be x squared, that's our function f of x, minus c squared, and we would like that to be less than epsilon, right? So this now is the first example where it is not totally and abundantly obvious straight away that this thing that we're considering is automatically less than epsilon, and indeed it might not be, depending on what c is, and so on. Okay? The thing to keep in mind now is that we're going to have to somehow take this inequality that we want, and we're going to have to manipulate algebraically this thing over here to the point where the thing we can control appears, okay? And the thing we can control is the absolute value of x minus c, okay? And so since this is a difference of squares, hopefully you can kind of see where we're going with this. But that's the problem. So let me put that at the top of the next board. Right, so we want the absolute value of x squared minus c squared less than epsilon. Okay, so let's start having a look at this quantity here. And what you want to do, first of all, is somehow make absolute value of x minus c appear. All right, and this is not too hard. So we've got absolute value of x squared minus c squared. That's the same thing as the absolute value of x minus c times x plus c from the difference of squares formula, which, through the basic properties of the absolute value, is equal to the absolute value of x minus c. That's good, because we're allowed to control that and make it as small as we want, times the absolute value of x plus c. That's somewhat less good, because it's a bit of a moving target, right? Certainly we know what c is, that's a fixed number, but x is moving around a little bit, okay? And similar to the case of limits, it would be great if I were able to say that I can replace this quantity here, this absolute value of x plus c, with just a constant, okay? Because that would say that, well, I would like absolute value of x minus c times a constant to be less than epsilon, and then it's pretty clear how small the absolute value of x minus c ought to be, okay? So what do we do? Well, this is similar to the situation in the case of limits of sequences, where in order to kind of get a handle on what's going on, you might have to make an initial guess at what your capital N of epsilon is. And that initial guess is not designed to make things turn out perfectly. It's designed to give you a little bit of control over some of the trash, algebraic trash in your expression, so that you can replace some of that trash with a constant. And then you go one step further and choose a much more refined and possibly larger value of capital N of epsilon to finish the job. Okay, so that's what we're going to do here, except now instead of, say, capital N1 of epsilon and capital N2 of epsilon, we are instead going to have a delta 1 of epsilon and a delta 2 of epsilon. And the idea is that by setting a something like, let's go ahead and do it. So let's set delta 1 of epsilon to be equal to 1. Right? In other words, let's insist that the absolute value of x, the absolute value of x minus c be strictly less than 1. Well then, that doesn't tell you exactly what x is, but it puts a pretty short leash on x, okay? It tells you x cannot stray particularly far from c, and that will be enough for us to get a handle on how big this thing is here, okay? So we set delta 1 of epsilon to be equal to 1. So if x minus c is less than delta 1 of epsilon, which is equal to 1, then how big can this possibly be? Well, I can say that the absolute value of x plus c is always, by the triangle inequality, less than or equal to the absolute value of x plus the absolute value of c. Okay? And what I claim now is that furthermore, the absolute value of x cannot be any bigger than the absolute value of c plus 1. Okay, so I'll draw a picture for that, but let me first just write it in here. Okay, so this is what I'm claiming, that because of this statement here, I can say that the absolute value of x is strictly less than the absolute value of c plus 1. Again, in the interest of continuity here, let me just erase part of what we've written so far. Whoops. Okay, so if you draw the number line, here's 0, let's say here's c. By insisting that x satisfied this expression right here, what you're really saying is that x has to lie somewhere in this little interval here of width of radius 1 around c. So I don't know, maybe there's x. But it should be pretty clear from the picture here that the absolute biggest that x could be is still strictly less than, well, in this case, c plus 1, but since c is positive, that's the same thing as the absolute value of c plus 1. Maybe c is a negative number, in which case you can take this whole picture and draw it on the other side of 0, okay? But in that case, you will still see that the absolute value of x is strictly less than the absolute value of c plus 1. Okay, so the upshot of all this is that as long as the absolute value of x minus c is strictly less than delta 1 of epsilon equal to 1, then you can say that the absolute value of x plus c is strictly less than 2 times the absolute value of c plus 1. Okay, so the absolute value of x plus c is less than a constant. All right, and then this will allow us to finish the problem. So if the absolute value of x minus c is less than delta 1 of epsilon, then the thing that we would like to be less than epsilon, the difference between f of x and the limit, is at least strictly less than absolute value of x minus c times this constant, 2 times the absolute value of c plus 1. We want this whole thing here to be less than question mark epsilon. And I'm allowed to make this part as small as I want. So all I'm going to do now is choose another delta, a delta 2 of epsilon, that says that this guy here should be smaller than epsilon divided by this constant. So set delta 2 of epsilon to be equal to epsilon divided by 2 times the absolute value of c plus 1. And then also set, so we're going to do the same sort of thing that we did. So when we were looking at sequences in series, right? Well, let me get on the other side here. When we were looking at sequences in series, sometimes it was necessary to choose an initial capital N1 of epsilon that did one thing for us, and then choose another capital N2 of epsilon that did another thing for us. And then in the end, if we wanted everything to work all at the same time, we had to choose our capital N of epsilon to be bigger than the maximum of N1 and N2. This is in the same spirit, but now we have 2 different deltas. We've got delta 1 of epsilon that allows us to get control over this term here. And we've got delta 2 of epsilon, which is going to finish the job. We want the consequences of delta 1 of epsilon and delta 2 of epsilon to both hold at the same time. Okay, and therefore what we're going to do is choose our delta of epsilon to be equal to the minimum of delta 1 of epsilon and delta 2 of epsilon. All right, and there endeth part 2 of the answer, right? You've analyzed absolute value of f of x minus L, and you have figured out what delta of epsilon ought to be. And then finally, we've got part 3 where we tie things all up nicely. Let me try and... Okay, so part 3. So we would just say with delta of epsilon as above, if it is the case that the distance from x to c is less than delta of epsilon, then the consequence is that the absolute value of f of x minus L, in our case, equal to x squared minus c squared, is first of all less than x minus c times this constant, 2 times the absolute value of c plus 1, and this is thanks to your delta 1 here, and subsequently less than epsilon over that constant times that same constant. That's thanks to your delta 2. And of course, then these two constants will cancel out, leaving you with epsilon. And that, by definition, tells you so the limit as x approaches c of f of x is equal to c squared, as required and desired. Okay? I've run a little over, so I'll leave it there. We'll do some more examples next time, but until then, stay safe and wash your hands.